I find myself in a situation where I need to understand basic math concepts to grasp neural networks. It appears that a solid understanding of vector and matrix calculus is essential. As a trained neuroscientist, I am uncertain about the accuracy of my explanations. If you spot any errors, please provide feedback. Neural networks can often be seen as functions with adjustable parameters. These functions take inputs in the form of vectors, matrices, or higher-order tensors and generate outputs. During training, a loss function like cross-entropy loss is utilized to measure the error in the output. The network's parameters are then updated through gradient descent, which involves calculating the gradient of the loss function with respect to the parameters. Understanding the organization of weight and data matrices is crucial when working with neural network packages. It is important to clarify whether each input vector in a data matrix X is represented as a row or column. Similarly, it is important to define how the weight matrix is structured. For a layer with n inputs and m outputs, the weight matrix can be represented as a matrix of shape, M, N, where each row corresponds to a neuron and each column represents an input connection. Alternatively, the weight matrix can be represented as a matrix of shape, N, M, where the roles of rows and columns are switched. Let's explore the weight matrix convention used by TensorFlow. We will create a custom function for matrix multiplication. After importing the necessary libraries, we define a model and display the shapes of the connection weight and bias vector. We then define an input, calculate the output, and compare it with the results obtained using our custom-defined function, as well as NumPy library. PyTorch follows a different convention. However, the weight matrix is transposed before computing the output. We will try to follow the following notations. Lowercase bold letters represent vectors. Elements of a vector are denoted by italic lowercase letters with subscripts. Uppercase boldface letters represent matrices. Elements of a matrix are denoted by italic uppercase letters with subscripts. Now, let's delve into useful formulas in matrix calculus. There are two common conventions in matrix calculus: the numerator layout and the denominator layout. The numerator layout has dimensions equivalent to the numerator, while the denominator layout has dimensions equivalent to the denominator. It is crucial to maintain consistency when applying these conventions. Here are some definitions in these two layouts. The Jacobian matrix is a matrix of first-order partial derivatives that describes how a vector-valued function changes with respect to its input variables. The chain rule is effective for scalar equations and index notation but can be problematic when applied to matrix notation, often leading to errors involving transpositions and dimension mismatches. The most reliable method for calculating gradients in matrix notation is through differentials. For vector functions, we have: if you are unsure about matrix derivatives involving the chain rule, simplify by breaking everything down into components. Let's consider an example. Applying the chain rule, we get equation. Alternatively, we can express the calculations in terms of components. With 3 elements in Y and 6 elements in W, there are a total of 18 combinations between Y and W. The formula presented here summarizes these combinations. To simplify the concept without using complex math symbols and nested summations, refer to the figures on the right. The final result can be expressed using either indices or matrix and vector notations. In summary, this formula can be used to calculate gradients in a neural network when it is applicable. Let's define the loss function as the dot product of the error vector g. Then we can calculate the derivatives of L with respect to y. Based on the formula, we arrive at the final result. If x and y are row vectors, the final derivative of y with respect to w takes a different form.